So this video series is turning out to be pretty long. Again, we're going for a 1930s portable CW station. I'm going to be operating on the 40-meter band, and we have our portable transmitter, which will be self-contained with internal batteries, and our portable receiver. You guys remember the Scotty Regen, and this regenerative receiver is mid-30s vintage. It also will be battery powered. I'm doing the transmit receive switching here. When you're putting a station together, it's more than just the transmitter and the receiver though. We have to consider all parts of the station. How are we going to do the monitoring of our signal, for instance? Is the keying going to be okay? Is the receiver going to be overloaded during the keying? How are you guys actually going to hear what's coming out of my headphones? I have to have a system where you can actually hear the receiver to hear both sides of the QSO. Also, station is defined by one particular thing we've been ignoring. It's called an antenna. What kind of antenna should we use on the air for a Parks on the Air CCC style from the 1930s? Think about that. What kind of antenna would you use back in the 1930s? This is all about putting the station together, getting the power, getting the wiring, everything all set up. We'll do a little test in the backyard to make sure the system works, and I'll bet we'll find some things that don't work, and we'll have to make some adjustments. But I hope you guys are enjoying this little foray into portable operation in the 1930s. So here's the basic setup. I have the new converter and the battery installed, with the filter on the output. Now I'm using a 12 ohm series resistor because I'm not really that concerned about filtering, but I think the 12 ohm going to the 100 microfarad will work okay. Not much drop there. And it makes it easier on the regulator to adjust when I go key down. Now I did notice something. It's charging okay, but I noticed that as soon as I attached the battery, this green LED came on over here. And I measured the current drain, and it's 15 milliamps. So even though I have an external switch that switches the power supply on and off, the power supply is always drawing 15 milliamps. Now if I were to remove that LED, it might go down to, I don't know, 5 or 10 milliamps. But I don't like the idea that there's always a load on the battery. And of course, over time, that would completely discharge the lithium-ion battery. So I think I may have to put in a master switch, a master on-off switch for the battery itself, just so I can keep the charge on there. And the way I'll probably do that is I'll add the switch over here in this blank part of the case, and it will be attached to the box, but it will simply stick out the back, and I can flick it on and off from the back of the case. No need for a nut or anything back there. It's just going to be a toggle switch that kind of pokes through a little bit, and it's kind of a let's shut the battery off for good kind of a switch. I did not expect I would have to do something like that on the primary of the battery. I thought the on-off switch or the activate switch on the power supply would handle that, but apparently that's a low-level switch, and some of the circuit is on, in other words, at all times. So all those unknown unknowns are being found again as we put together the power supply for the transmitter. Okay, I now have the on-off switch. It's a nice heavy-duty short bat toggle, and when I turn that on, the green light comes on, and now we have the 15 milliamps going into the circuit. It will not activate and put out the high voltage, however, until the two leads are shorted here, the front panel transmit switch. So even though the unit is on, there's no high voltage on the output yet. Now I do not want the battery flopping around, so I'm going to be using 3M VHB high bond tape to tape the battery in place to make sure that it's not going to be vibrating around and hitting something. Okay, we're all set to put this module inside the transmitter case, and like someone said, it's quite a mix of modern and ancient technology. Okay, so that guy will go in there something like that, and I'll just stick the D cells over in the corner. High voltage, and lighting up the tubes with a pair of D cells. A little bit of Swiss cheese in back of the unit, but here's the high voltage power pack with its on-off switch. Let's just say we put this back here. That sticks out, and we can mount the screws. Of course, a quick test before I install this thing, that's for sure. Want to make sure this is working. Also, I want to pull this and see if the bleeder will work. I have a 270K 1 watt bleeder, and it is bringing the voltage down. Okay, the Steampunk receiver that I'm going to be taking to the field, I'm testing it to make sure it's okay. A couple of little modifications to it that some of you guys probably will like, and others will not like. First of all, you can see I've added a control to the right of the on-off switch. That is a throttle capacitor. Now this effectively gives me 3 degrees of freedom with regeneration. We have the rheostat in the back, which controls the filaments on both tubes. Then just below the tuning dial, I've got the B plus adjustment. That's a potentiometer in series with the B plus to the detector stage. So that's 3 different adjustments that all influence the regeneration. And it's amazing how you can optimize this thing with three controls. The other thing I've changed since you saw it last is instead of using the trimmer on the input as designed, I've got a single loop of wire at the bottom of the plug-in coil that's attached to the coax. And as you can see, there's an alligator clip that grounds it. This single loop primary that I've added to the regeneration, the main coil and the ticklers on top, you can see it to the left. This is really improving the performance of the receiver. And of course, a single loop is very light coupling into the regen, which preserves the Q, compared to using a trimmer. So I'm probably going to go this way when I go to the field. Now, of course, you can't hear what I'm hearing in the headphones. Okay, so I'm going to come up with a way to take that output from the headphones and amplify it to the level where you could hear it in a speaker, so you guys can tell that I'm picking something up. Or maybe I'll distribute the audio somehow and get it into the video, but you guys can't hear what's going on. You can't hear the code stations I'm trying to pick up, and I need a way to do that demonstratively on the video. So there will be some kind of an amplifier or audio coupler or some kind of thing on the receiver so we can get some audio out of it in the field. I don't know if we can hear this or not. So anyway, I'll find a way to amplify this thing so you guys can hear it. Do you guys know what the most important part of any transmitter system is? That's right, it's the antenna. Up to now we've been ignoring the antenna, but I want to address the type of antenna that they might have used 80 or 90 years ago. Now today, for Parks on the Air, we have this end-fed half-wave, EF-HW, which is very popular. It uses a coaxial feed with a Ballon transformer, feeding an end-fed Hertz antenna. Now the end-fed Hertz antenna is always a multiple of a half wave, and the half-wave Hertz was developed for use on Zeppelins because if voltage fed on the end, it doesn't require any ground system, and you could feed it with something like open wire line of 600 ohms or 1,000 ohms, something like that. So QST in September 1929, they took an idea that had first been published in the 1925-26 handbook and in QST, and they finally got it fully developed. And this was published by Lauren Wyndham, LG Wyndham, in the September 1929 edition of QST. Now, LG Wyndham did not actually invent the antenna. but he certainly promoted it for ham use. And even though there were other people that did the formal work, and they were publishing in scientific journals, this got published in QST actually before those articles became accepted by the scientific community. So LG Wyndham, Lauren, 8 Gulf Zebra, later W8GZ, purported that you could feed a half-wave Hertz antenna in a place where you could use a single line feeder, and that feeder would be essentially untuned and could be made any length, and it would feed the antenna at such an impedance that you would get the proper current node in the center of the antenna. This is a really interesting design for an antenna because it's a 500 ohm type feed wire. So a single wire feed at 500 ohms. And this lends itself to tube type equipment. Tube equipment works a little higher impedances than solid state equipment. So 50 ohm coax is not necessary when you're using tube type transmitters. Tube type transmitters like to use 600 ohms or 500 ohms. So 600 ohm feed line works out very well. But I'm going to try the OCFH, the off-center fed Hertz. Off-center fed Hertz. The OCFH is going to be our Parks on the Air CCC camp antenna. Now, by doing plenty of experiments with current meters, Wyndham found that on 40 meters, and by setting the half wavelength according to this chart, let's say we wanted to do 7050, we follow this over and it says we've got to have 67.5 feet for the half wave element, and that we would put our feeder at approximately 9 feet 5 inches off center. So it doesn't matter which way we go, but off center, we're going to measure 9 feet 5 inches, and we're going to solder the single wire feeder at that point. That's going to come down to the transmitter terminal, and then all we have to do is make sure the transmitter's output is set for 500 ohms or 600 ohms, something in that ballpark. So the first thing I've done is I've measured the antenna and cut it to 67 feet 5 inches plus a couple of loops to attach the insulators. And the next thing I'm going to do is find the center of the antenna and measure 9 feet 5 inches off center, and I'm going to attach our single wire feeder. I'll probably make it 50 feet long to start with, and we can cut it down to what we need once we get at the Parks on the Air location. Okay, I have the middle of the off-center fed Hertz, and I'm going to measure 9 feet 5 inches off one of the legs, and then make a mark there, and that's where I'll attach the feed line. The feed line is just a piece of number 14 wire that's going to come straight down to the antenna terminal on the transmitter. Okay, at 9.5 feet, I'm going to make a mark, and that's where we will attach the feed line. Okay, our feed line is attached. It's soldered, and I'm going to relieve a little bit with some tape. Remember, this is just a portable setup. Just has to work for our little test that we're doing. Ready to go. Okay, just as a test, I've brought the Wyndham antenna up at around the 20-foot level, and I got plenty of feed line to come down to a table. And I'm going to try this thing in the yard, of course, before I go to the field, because I have to make sure the transmitter will load into it properly. I might have to change the tap on my output coil. And I won't be driving a ground rod, out on the park property. I'm going to be erecting a counterpoise underneath the antenna. This is approximately 70 feet underneath the half-wave radiator. Now, the result should be a very efficient half-wave, near vertical incidence type radiation pattern. Okay, we have Wyndham's chart, but let's try modeling with Mamanagal. I have this saved down in the Wyndham area, Wyndham 40 meters, there it is. Open it up, and yes, that does look like a Wyndham antenna. Good. Let's look at the geometry. 7.05 megahertz, and it looks like we have 7.2 meters one way and minus 12.6 meters the other way. That's 65 feet total, which is a couple feet short compared to what Wyndham had on his chart, but this gave me the best performance. Let's go over here to calculate. I have a real ground set up, and I'm closer to the ground. Okay, we've got a really good SWR, wavelength of 42.524 meters. Now let's see what impedance that we're into here, 300 ohms. 300 ohms because we're closer to the ground. Now if I did it at 600, have a higher SWR, but still acceptable. Normally you use 400 for a Wyndham, and then if we do 300, it's almost perfect. Okay, so if the antenna was high in the air and not close to the ground like it is, you probably could use the higher impedance, but 300 is what this one likes to see. Let's look at the currents. Okay, you see this little gap between the two currents? That tells me that I haven't exactly got it perfect, the position here, but I'm very, very close. If you have this wrong, you'll have a big step function here between the two wires and the current. This is actually quite good. So if you can get something that looks like this, you're in the right ballpark. Now this is a cloud burner. You can see it has a very high angle of radiation because we're so close to the ground. This is exactly what I'm looking for. So there we go. We have the Wyndham modeled. It's going to work okay for us. It's going to be a fine portable antenna for our parks on the air, civilian conservation corps style.